Hello, and welcome to RF Design Tutorials, a playlist where we talk about practical RF and microwave circuit design. This is Tutorial 8 on Distributed Impedance Matching Network Design. I hope you are following the previous videos on impedance matching. This is part 3 video in the same series, and in this Tutorial 8 we're going to talk about distributed matching networks. Here is the detailed agenda of the topics what we will cover in this tutorial. And as you can see, we will start from something very fundamental and walk our way through to Gerber export. And we will talk about how to export this file for fabrication. So plenty of important topics for you. And I hope you will stay till the end of this tutorial to make sure you pick up all the tips and tricks which I'm going to give you in this tutorial. And not to forget, there are many practical considerations which we will talk about during the video. So it's very important that you watch each of the topics with great interest. Now before we just start, subscribe to my channel. If you already subscribed, click on the bell icon to make sure all the notifications are enabled. Don't forget to hit the like button if you like the video, and click share button so that you can share it to your friends and colleagues. Another request, please go ahead and post this link to various social media or forums you are a member of so that the entire RF design community can get benefited with the help of these tutorials. And I thank you in advance for doing so. All right, so let's dive in. Plenty of topics ahead, so it will be slightly longer tutorial, but I will make sure you get every minute's worth when you spend time on watching this tutorial. All right, so we are going to use the same as parameter file which we used in the last tutorial, and we have input and output, in Smith chart component placed. And in the last tutorial, basically, let's say for this input impedance matching, which is match one, we use components like series inductors and shunt capacitor to build as kind of LC topology, and we talked about all the Q circles and all those considerations. So here our objective is not to design matching networks using those LNC approaches. We already discussed plenty of things about it, but we will explore how can we implement a distributed equivalent of this kind of network. But remember, no matter what you do, all the distributed transmission lines eventually are representing some form of inductor and capacitor. And these are the primitive components. It's just that we are going to realize them using distributed transmission line theory. All right, so let's delete some of these components. Now, before we start, just notice few things here. If you have a series inductor, you can see the locus moves, in a constant resistance circle, something like that in a clockwise direction. If you have a shunt inductor, you end up moving counterclockwise. If you have a shunt capacitor, you start moving in a capacitive zone, and if you have a series capacitor, you move in anti-clockwise. So just remember some of these fundamentals because we will use them in our distributed matching network theory. All right, for distributed matching networks, we basically have three components which we can utilize. One is the series line, and then you have shunt, open circuit stub, or a short circuit stub. So using these three, we can replicate the behavior of all these components which we have, for the lumped element matching. Now, if we take a series line, basically the behavior is quite similar to the series inductor. However, you can see the series inductor was going through in this direction, and a series transmission line is kind of bending far too early compared to inductor. And the reason for that is, if you remember in your theory, the equivalent circuit of a transmission line is basically LC network, right? And the default, impedance for these transmission line, as per theory, what we use in a Smith chart is always 50 ohm, and that's why you have a particular trajectory. However, if you make this line little more inductive, now how are you going to make this line more inductive? By increasing this impedance, and you all know that. So for theoretical sake, let's say if I make this impedance to be 300 ohm, right? Which is not possible practically, but just for theory's sake. Now, as soon as I make it 300 ohm, you can notice now the series line starts behaving like a series inductor. Isn't that cool? But that's what the theory is, because now with higher impedance you will have a very thin line, and when you have very thin line your capacitance will become almost negligible, so this line will start behaving like a pure inductor. So first practical tip for you to consider. Now when you have the series transmission line and you want to move in a counterclockwise direction towards unity circle, what component can you use? Well, you can use open circuit stub or a short circuit stub. So in open circuit stub, as you can see, classical by theory, you can move, the locus pretty much like how you were moving with the shunt capacitor. Now again, this open circuit stub, the impedance by default is 50 ohm. However, to make it more capacitive, let's say here with 50 ohm impedance and 35-degree electrical length, which if you want you can convert in lambda, is taking your point from this point to this point. Now what if we make it more capacitive, and how do we make any line more capacitive? Is by decreasing the impedance. That means we make lines wider, and by putting 20 ohm, and you can see suddenly now with the same amount of electrical length you can get much bigger impedance transformation. And if you wanted to reach to the same point, let's say at similar location, now we only need 12-degree instead of 35-degree. So immediately you have 1/3 of space saving in your overall circuit design in terms of the length of this stub, right? So the key fundamentals to take away here, wherever you need inductive behavior during transmission line matching, increase the impedance of the line to let it behave more like inductive as far as you can go. And wherever you need capacitive action, try to reduce the impedance. That means make wider line in your PCBs to get more capacitive action. Well, that's good in theory, but the point is how low impedance can we go and how high impedance when we can go. Well, that can be very easily done by using line calculator in ADS. So here under tools, line calc, if you start line calc, now this is like a transmission line calculator, and you can compute various kind of transmission line here, strip line, microstrip line, suspended strip line, and so on. But right now we will focus mainly on MLIN, which is microstrip line calculation. And here we can enter our dielectric specification. So here you can see I have entered specification equivalent to Rogers 4350 substrate, and I selected the height as 20 mil because I'm going to do design over 5 to 7 gigahertz. So I found that appropriate. Now ER is 3.66, conductivity is copper. The metal thickness could be 35 micron, which is 1 ounce copper, or 17 micron, depending upon what you're using. And the loss engine is 1 e raised to minus 4. So you can enter your own dielectric over which you may want to do this design. And now for our analysis, we can enter our frequency, which right now is 6 gigahertz, which is my center. Now, by giving the physical parameters, I can click on analyze and it can compute my electrical, parameters, or I can feed electrical parameters, click on synthesize, it can compute my physical parameters of this transmission line, right? So we are going to use this calculator. So when I contact Fab House, they tell me that on this dielectric, the minimum width they can, accurately fabricate is 0.2 mm. Now 0.2 mm line on this particular dielectric will represent certain Z0 or the characteristic impedance. So now let's calculate. If we hit this analyze button, now ADS will go and analyze it and tells you it's approximately 106 ohms, or on a lower side, safer side, 105 ohm. So that's the highest impedance you can go. But let's say if you find a fab house which can go down to 0.1 mm or 100 micron width, and if you try to analyze it, then you could design your matching networks with 127 ohm impedance. And higher you can go, lower line you would need. So these are very important considerations to take. But on practical, based on my experience, most of the fab houses can go up to 0.2 mm. But if you're lucky, your fab house will can go much higher than that. All right, so this is one anchor point I take away from here. The second anchor point is how wide line can they etch. So usually, roughly on a typical fab house, they can confidently do something like 3 mm, but usually they don't have any upper limitation, but mostly they kind of recommend you to use only up to 3 mm. Now, if we give 3 mm, we get another bound, which is more for capacitive line, and here we can notice lowest I can go is around 24 ohm, which can be confidently, printed on my PCB. These are very important practical considerations which you need to take before you jump in to the world of, impedance matching. Well, now I know my bounds. I have my source and load, and remember this load is same what we used earlier, 26 minus J 6.7. If you haven't watched tutorial number 6 and 7, please go ahead and watch that. So we lock load and source, and let's go ahead and change this line to what we calculated. So 105 ohm is the maximum impedance I can make. And now using that concept, I can go ahead and truncate this line. Now for this line, I just calculated minimum I can go is around 24 ohm. So I will restrict myself to 24 ohm. All right. Now rest of the fundamental remains pretty much the same. So I insert a line. Now this line, I need to modify the impedance to be 105 ohm, and then I can just proceed with the regular design. So here, let's again insert one more. So it's like a two-step matching network, which I'm trying to design. And this step again, I can keep it like 24 ohm as the reference impedance, and then adjust this line length. So now, in theory, and now I can set up my frequency graph here. So 7E9 starting from 5E9, which is 5 to 7 gigahertz. And now I can look at the minimum reference as minus 10 dB. And I can see all across I'm at least getting minus, better than minus 15, minus 20 dB. So this network is pretty much now good for now. But here comes the another practical design aspect. Now look at this circuit here. The network which we are trying to design is here. At the input side, if nothing else is connected, let's say I'm only designing this circuit, so you will have an SMA connector which will come at the ZS point or the source point. And on the output side, you will have the lead of this component. And this is like a SMT component. The lead has to be placed on that impedance network line. Now, if you refer to this topology, you have no series line at ZS point here. That means where are you going to mount the SMA lead, right? So that you need to account for. That's practical tip number 3 rather. And then on this side, because this SMT component lead will land, I need to make sure if I want to utilize this line for my component lead placement. If I'm going to have another footprint for this S2P which I want to associate, and it already has a lead to mount, then I don't need to worry on this side because the footprint will start from this location. But sometimes people want footprint to land directly on this line so that they can even reduce the size. So if you want the footprint to be landing on this line, then this impedance has to be set as per the width of this pin which you are going to have. For now, I'm going to assume this is fine. The only thing I need to do here is this is not going to work, and I will need to add a series line, and the series line will have this kind of transformation. So I will extend it a little bit, and then I will move my line little down till I hit this unity point, and now I can add a series line here, and then I can adjust it so that this line kind of crosses the the unity point. And again, you can start playing with impedances a little bit. For example, if I make this impedance a little high, for example 70 ohm, again depending upon how much width are you going to need, and then you will have that point crossing the unity point. And now you have the similar kind of matching network here. So now you fulfill all the criteria. Why it is important to keep track of all these things? Because if you don't keep track of these, after you're done with the entire circuit design, you insert a 50 ohm line, and suddenly your match will get disturbed and you need to redo some of these design. All right, so with this theory, we are done. So we'll go ahead and build ADS circuit. If we push inside now, I have these ideal transmission lines now, and they are not physical microstrip lines yet. They are all ideal transmission line, as you would expect as the output of Smith chart. So you have the impedance and you have the electrical length, or if you want to consider it as in terms of lambda. Right, so similarly, we need to calculate the output match. So let's go ahead and simulate the circuit as it is. And now we notice the output impedance we need to match is around 44 ohm. The input match has done its job, and you can see sharp null at 6 gigahertz for S11. That means there was almost a perfect 50 ohm match. Right, for output impedance, like how we did earlier, we go to match 2. In match 2, my source has an impedance of 44 ohm, and then the load has 50 ohm. Right, now we can again start to use the same kind of topology, and remember we will always have a series line because the load is this side, and again there will be an SMA here. So we'll go ahead and insert a line, and that line, because it's by default 50 ohm, it will get stuck there. So I will click on this line, make this impedance to be slightly higher, let's say 70 ohm, and then I will give it some length, for example 20 degrees, and now I will have some line moving in that direction. So first criteria fulfilled, 20 degree will be just sufficient to launch an SMA line. Now we add a shunt capacitor like previously how we did, and this shunt capacitor we can go down to 24 ohms. So I'm not going to describe each and everything. I think you got the point. And now I can add another series line to this point, and again this series line I can keep it as 50 ohm or increase the impedance. Again, it all depends on what convenience you have, and we can zoom into this portion of the Smith chart to make see things clearly. So I have another line, and then we will add one more shunt line, and again we can increase it. Don't directly cross. I could have crossed here, but again you see you will miss the series line point here, and we need to bring it up. So we'll go ahead, increase a little bit, go a little down, and once we are a little down, we will add a series line of 50 ohms so that we hit that line point. And now I have practically feasible circuit here. All right, so we'll go ahead and build ADS circuit. So now I have both input and output matching network done. We will go ahead and run simulation and see how's the performance. Now at center point, you can see both input and output. That means S11 and S22 showing a good response. However, we need to optimize the matching network to cover the entire frequency band of 5 to 7 gigahertz. And we already learned how to do that in previous video. And let me go ahead and insert a template and optimization. And it optimization has two goals: better than minus 20 dB. I have optimization controller. Now, if you don't know how to work with templates in ADS, please go ahead and watch another tutorial which talks about templates in ADS on my YouTube channel. So we'll go ahead into simulation variable setup under optimization. Now this transmission line which has 50 ohm, I'm not going to disturb them. So I will only optimize their electrical length, and rest of the lines I can go ahead and optimize both impedance as well as the electrical length here. So let's go ahead and activate all of these relevant parameters. Right, so we are almost done. Now another constraint, you see, we need to take care of constraints. So minimum, we cannot go below 24 ohm. So we will set the minimum constraint on the impedances to be 24. So 35 is fine, and 12 cannot be accepted. So 24 ohm, 12 cannot be accepted. So 24 ohm. And on the higher side, we know we cannot go more than 105. So we'll go ahead and make sure the maximum constraint I have is 105 ohm. So it looks all okay except one place here. All right. So once we have a right constraints in place, because anyway, there's no fun in optimizing your circuit for the values which you can fabricate, right? So let's go ahead and kick start optimization, and you can see how quickly it kinds of nearing my desired point. And there are few guys like in terms of length, it is hitting the max limits. So if you want to further improve, we can go ahead and increase the limits here by pausing the optimization, clicking on edit variables, and here we can go ahead and give them a little more kind of range, for example 100 degrees, and then we can continue. All right, but in the interest of time, I'm going to stop here. I will assume this is what I wanted. I'll update my design so both of these networks are updated. So let's go ahead and run simulation. And now we can notice the optimized performance with return loss very close to minus 20 dB. So all in all, pretty good. So now what's the next step? Well, the next step is to convert these electrical lines into a form of physical transmission line. Now to make my job easier, let me show you one network, and then I already have the finished network which I'm going to show you, but this is very important to understand. So here is my input matching network, and similarly I can go inside and I can get this matching network, Control C, come up, and Control V. So basically I have both input and output matching networks in place here. Now in order to convert these lines into a physical microstrip line or a strip line, again depends upon what kind of network you are designing, we can again use line calc, and line calc has all these capabilities built in. However, I'm going to use this line calc, kind of process quite a bit because I have multiple transmission lines here. And I don't want to go to this menu all the time again and again. Rather, I can create a toolbar or a custom toolbar here for myself. The way we do that is go to Tools, Hotkey Toolbar, and here under Toolbar tab, I can go down and you can see all the toolbars which you currently have active here. They are all displayed. And now I can create my own toolbar, call this as line calc or whatever you want to call it. And now this is empty toolbar. There is no button associated with it. But now you can see there's a placeholder here ready for you to add things. So now you go to the menu from where you want to get the buttons on this toolbar. So the line calc is available under Tools Line Calc, and it has 5 functions here or 4 functions here. I will start from the bottom, insert, and keep picking one by one and keep inserting, and you can see the components have started appearing here. So this way I will insert all the components. Now for the command which has a bitmap will appear. Otherwise directly the text will appear for the things which you don't have the icons here. But doesn't matter, I get my job done. Now in order to use line calc for these applications, I can create an equivalent microstrip network for here. So I can go to T-Lines microstrip library, and from here I can first place a microstrip substrate where basically I need to define my substrate specification. So I'll go ahead and type same 20 mil 3.66, conductivity of 5.87. You can just keep pressing enter and areas will start moving into another field for editing. This is 0.035 mm or 35 micron, and loss tangent is 1 e raised to minus 4. So that's my stack up definition. The second thing I could do is simply use this mlin component, which is microstrip line component, and I can create a network which is very similar to that. Don't worry about the values. That's what we will calculate using line calc. But idea is just to place this structure here. So now I have a structure which is representing very close to what we have here, and we can start wiring them up together, or you can keep it unconnected, doesn't matter for now. All right, so now once we have this structure in place, these components in place, I can go ahead and now start using line calc for my calculations. All right, so to start line calc, I can click on this icon here. It says start line calc. And now let me put them, side by side so that we can see both of them together, and it makes my job little more fun. And let's zoom in here. Now, the first thing I would like to do is send this transmission line to line calc. And that can be done by selecting this line, send selected components to line calc. And now notice this width and length of this transmission line gets transferred here along with the M sub 1, which is name of our substrate here, right? So all the relevant parameter gets copied. Now what I want this line to be, I want this line to be this impedance. So I go ahead and enter that impedance 100 ohm, electrical length of 24.5 degrees. Click on synthesize, and now it will compute the physical parameters on this dielectric. Once it is computed, I can select that line again in case I deselected it. And I say update selected components from line calc. And once I do that, this value will be updated from what we calculated. Simple, isn't it? All right, so let's select another component, send this component to line calc. And now I need to enter this number here. So 24 ohm, and then electrical length of 19 degrees. I compute the parameters, and then I will update this component parameters. So this way I need to keep on doing it for rest of the parameters. After that is done, remember, if you consider, here's the practical tip number 4. If I have this kind of microstrip line and I connect this, I simulate like this, you are missing some effects here. And the effects which you are missing is basically this junction discontinuity. And in RF microwave, the junction discontinuity is the main thing which you need to take care. So in ADS, you have various junction models. So here we have a T junction model, which is more appropriate for this structure. So let me move the text here. And now we can connect at every junction point the suitable junction model. So this discontinuity model, when we run a circuit simulation, will compute the reflections or the distortions or the impedance mismatch, which is going to occur at that junction. So very, very important tip to remember. Never ignore the junctions. So you have T junctions, you may have cross, and when you are connecting two dissimilar line in series, you have this step calculation. So all these junction models are going to be very, very important. And if you make four-way connection, you also have this cross model. So you could make like a four-way connection. So never forget to use those. Never ignore these. These are the ones which will kill your entire circuit performance. So once we do that, the next thing I'm going to do, because later I might need to optimize this circuit to retain or regain the performance of my matching network, I'm going to declare all these values in a variable. And when I declare W1, W2, W3, L1, L2, L3 and pass those numbers into these transmission line, it will help me to make sure when I change this W1, W2 or W3, and if I use the same variables in this discontinuity model, this will keep the entire design in sync. So this way, when you make changes, something like this, say W2, this is W3. And in ADS, if you have more than two components, how do you compute which is third terminal, which is second terminal? Always look at this hash line. The hash line indicates first port or first pin, and then you go in a clockwise direction. So this will be 1, this will be 2, and this will be 3. Another important thing to remember. And if you had cross, we will follow the same fundamental here in cross. So if I just insert cross again, notice this is pin number 1, that will be pin 2, this is 3, and this is 4. So that's how you simply chalk out. Now, after we do that, we are going to re-optimize. So I have already done that. So let me, delete this component, or let me create a new schematic, and let's call it fixed design. And I already have finished a design. I have a template here. So here I have already done what I just described, and you can notice here. So you have the input matching network, which are these components with two stubs in place. And we have output matching network with two stubs and two transmission lines, one at each end. Now all these components you can notice are using a variable here, and the values which are 50 ohm, and I don't want to change them. I have declared that 1.11 mm, which is 50 ohm on this 20 mil Rogers toroid material. And I also have this W1 to W10, L1 to L10 variables, and all those have been assigned to this circuit. Now, if we go ahead and simulate this circuit, we can notice the performance of our matching network in presence of all discontinuities and using practical, microstrip line. And you can notice the match has distorted from minus 20 dB to something like minus 15 dB. But again, remember, we have the optimization goals. We have all these, component values declared as optimizable. We can go ahead and hit optimize. And now ADS will change the real width and the length of the microstrip lines and readjust your circuit performance to give you the desired goal. And again, as you can see, my error function is 0.02. That means I'm pretty close to meeting the goal. But again, in the interest of this video, I will pause this and I will say, okay, I'm pretty happy with what you have given me. Close, update my design. And now all these variables values are updated based on our optimization. And now if we go ahead and run simulation, we can notice the optimized performance where my impedance matching is better than minus 20 dB across 5 to 7 gigahertz. So pretty good. And also you can notice the same thing with the Smith chart. All right, so now this completes our first part of the tutorial. To quickly summarize, you need thinner line to produce a good inductive behavior. It helps you save some, design area by having a smaller lines. For capacitive action, you can go for wider lines. It will produce more capacitive action. And never cross the minimum and maximum limits of your impedances. Also, while designing these kind of network, always keep in mind what's going to come at port 1, what's going to come at port 2, and have a series lines appropriately connected. Otherwise, you will need to do that very late in your design when you realize something has happened. We also learned how to create custom toolbar to bring out certain, hidden, commands in the menu so that they are more apparent on your toolbar and you can quickly click on them and get your work done much faster. We also learn how to use line calc, how to convert transmission lines from electrical equivalent to a physical equivalent, or vice versa. By entering the physical, parameters, we can compute the electrical properties. And there will be a separate video on line calc because I haven't even covered 5% of the capability of line calc. However, go ahead and unlock the full potential of using line calc. Try out line calc on your own. And also then we talked about practical microstrip implementation because remember the importance of discontinuities using microstrip step, T or cross junctions as may be required in your circuit design. And then we performed overall design optimization. And now I have a very good circuit representation of my design. Now, let's talk about EM analysis of this distributed matching network and how we also take care of few practical layout considerations in order to avoid parasitic coupling and minimize future problem which might get thrown up by an EM simulation. And finally, we'll set up an EM simulation. We do a co-simulation. And then finally, we've prepared a final layout, which is more suitable for fabrication. And then we will go ahead and export Gerber file from our layout. All right. So once we have this final design, if we want to generate a layout from this, there are various ways of doing that. One of the way is you can go to layout. You can place components from a schematic to layout. That means one by one, you can start placing components from a schematic to layout and you can keep adjusting them as you are placing. But if you think you already have the right structure in your schematic, you can do that all things in one click. The only thing here to note is all these transmission lines have the footprints. So they are like P cells, no problem. But this S parameter file, right now doesn't have any footprint. But in this case, luckily, I don't need footprint because this is just like an SMT S parameter file. It will have two pins. One will land on this line and another will land on this line. So I just need something to replace this guy. So I'm going to go ahead and deactivate it for layout generation process. And from the T-Lines Microstrip library, I can just place a component here called gap, because basically I just need to insert a gap in place of this line here. So I'll insert a gap and select, and connect this on the other side, each side. And here width could be 1.11 mm. And now spacing, or S is the spacing. So I know this component is 2 mm, in length. So I'll just create a placeholder for 2 mm. That's it. Now, if you want to create the layout, just go ahead to layout, click on generate update layout, click OK. And now you will have the layout representation of your circuit design. You can notice your input line, your output line, and all these text shows you all that. But if you don't want to see the text, just switch off silk screen and silk screen 2, and you have this representation. This is your second step. This is your, the first step, and so on. So you have all the discontinuity models, all the, right models. But here I do see a problem. Ideally, this discontinuity should not go here. This should be truncated to this point here. And here it seems okay because this is the width and this is the right discontinuity. Do I have some problem here? And if I switch on the silk screen, I can see in T2, I probably have parameter mismatch. So let's go back into T2, which is this guy. And in this guy, I can clearly notice W2 is defined as W4. However, it should be 1.11 mm. So we go ahead and change it to 1.11 mm. Run a circuit simulation just to ensure this discontinuity hasn't killed my design. But here it looks like, the complete design goes for a toss. So we might need to re-optimize. So sorry about that. So this S parameter has to be active. So let's go ahead and run simulation. All right, minor implication, nothing major, but again, this performance is slightly worse. So I'm going to go ahead and re-optimize it a little bit. So click on optimize again. And now you see the importance of missing one discontinuity. Your performance was changed. All right. Now it seems that we are back to our original condition. We pause, we close, we update our design, and now we have the right parameters for the optimized result. All right, now we go ahead to layout, generate update layout, click OK. And now the old layout will be overwritten, and we do have this as parameter component. Let's delete it. So now if you notice, it's properly aligned. The width here is aligned nicely to that line. All right, so once we have the layout, let's go ahead and click the pin and start placing the pins. So these two pins are the placeholder where later I will connect my S parameter file. That's your input and that's your output. All right, now to set up a stack up, I can click on a stack up. And again, by default, if you don't have any stack up in ADS, you will get a template or default template. But in my schematic, I already have the stack up, so I could just simply import that. Remember, in my schematic, I already have this M sub design. Now, this M sub 1 can be imported into layout here. So I go to File, Import, Substrate from a schematic. And now I can just select which is design I'm talking about. So my design name is fixed design and the substrate is defined here. Click OK, and now you have the substrate. So the main conductor layer is conned, and then you have a whole layer, which is basically the conductor via. The rest of the layers which we are not using, we can ignore. Even if they are there in the stack up, doesn't make any difference to our layout. And it's a 3.66 ER, 20 mil substrate, and this conductor thickness, if we click on this conned, is 0.035 mm. Let's change it to millimeter. All right, so everything is pretty good. So I have fixed design as my template or the substrate file name. Let's close some of these and go back to our layout. So the key part of the setting up EM simulation, we need to have pin, we need to have a stack up, and both of these things are there. Click on EM, create a new setup, select your simulator. So I'm going to use momentum microwave. If you want, you can use FEM, and we already have tutorials talking about it. So we have substrates. We go ahead and use fixed design substrate. Ports are already connected, and I'm going to run simulation from 2 gigahertz to 10 gigahertz. Under options in mesh, I'm going to go ahead and increase the density to 60 cells per wavelength because some of these components are very small, so I need to make sure they get meshed properly. And in models, I will create a EM model, and also for EM circuit co-simulation, I'm going to open the symbol editor. Now notice your design has both a schematic as well as layout representation. So I need to generate symbol from the layout source, and I will generate a layout lookalike symbol, and you can define the distance between the pin. You click OK. This is how your layout symbol will look like when we place it in a schematic later. So let's go ahead and save it. Close this. And now we are ready to launch EM simulation. Click on simulate. It will take few seconds to run simulation. You can see the nice meshing which has happened for your layout. And once you have the results, this result doesn't make too much of sense because you don't have any S parameter connected right now. All right. So now layout job is done. Let's close this layout for the moment. Let's close this data display as well. Let's get rid of all these windows. Now I'm going to take the termination, the S parameter controller, the another side termination, and this SNP file from here. Control C, create a new design, and let's call it fixed underscore cosim. And now I have a new design. Let's paste those components here. And now from the main ADS schematic, main ADS window here, I can go and look at my fixed design. And in fixed design, I do have a symbol. This is the layout we just simulated to create this EM model. We drag and drop this symbol onto this schematic, and now we can connect these components at their respective places here. So let's keep them together. And this is what we call as EM circuit co-simulation, because part of your design is coming from the EM simulation. Part of the design is in your schematic, and we will dig deeper into this mode of operation when we go into the the LNA design. So we'll set up from 2 to 10 gigahertz, and this representation or this symbol, as you can notice here, has a schematic view, it has a layout view, it has a EM model view. So once we select the symbol, we click on this icon here, which is called choose view for simulation. And I would like to ensure I use EM model behind the scene. So it will fetch the EM results onto schematic. And when we hit simulate, we will see a combined response. So let's go ahead and copy the plots from our design here. So let's select Control A, Control C, and come back to this schematic and place it. And now you are seeing the response along with EM simulation. It's slightly distorted compared to the circuit response, but not by great amount, and you still have better than minus 20 dB kind of return loss. All right, so if I go back to my agenda, we covered up to this point. Finally, we have a topic of final layout and then exporting Gerber for fabrication. Now, sometimes, the RF guys, they can go ahead, let me clear the mesh. They can go ahead and fabricate it like that. But sometimes they want to insert copper pouring. They want to have ground on the entire side, and they want to insert the via hole for grounding, for the ground stitching. Now, if you want to do all those actions, it's very, very simple in ADS to do. We can just simply go to insert plane, which is representing ground plane, and we can define the clearance. So let's say I want to keep ground clearance by 0.5 mm from my existing conductor, which is drawn on Conlayer. And now if we go ahead and draw, let's switch on the grid snap. If you go ahead and draw the size of the ground as you need. Okay, so here I'm just doing a rough drawing, and now you have this ground conductor, okay, which is kind of how you typically do in a practical board layout. Now you only need this stitching hole here. So remember, in our stack up, we had a whole layer mapped here. So if you want, I can change the layer, entry layer to hole, and then we can just insert a kind of draw a circle. And this circle here, we can define the radius. For example, here, I want this, via hole to have radius of 0.2 mm, and I create one via. Now, once you have one via, you can create a via array by going to edit, copy, paste, step, and repeat. And now you can enter how many rows, how many columns you want. So here, for example, I want 4 rows and 8 columns. And when we click apply, you can see a barrage of via holes. So we can just go ahead and place those via holes anywhere you want in the design. And this single via hole, Control X, Control V, we can, cut and paste, and we can, because this is where the SMT body will be shorted, and I need to make sure I have enough, ground holes to ensure the body gets shorted. And reason why you are seeing this kind of hash line here, because ADS is, telling you, because we are in net saying your ground net is conflicting with these guys. Now this entire via hole, let me switch off everything and only switch on the whole layer. I can select all these whole layers from here, and then those whole layers or whole components. So let me select all this one by one, and this can be created into a group. So I can go to group, create a group, give it whatever name you want, but now this is like one entity, this entire array. So now if we click on any of these entity, you see this blue icon. If we click on that, it says net is overlapping. Do you want to merge? I say yes, and now those overlapping warning has gone. So now this via holes are also belonging to ground net. If you look in info, you will find that they are on net ground. All right. It doesn't make too much difference for your Gerber file export, but this is how you can just simply do that. Now, if you just right click and measure and make sure the corner snap point is on, and if you measure the size of our layout is like 14.2 mm by 14.2 mm, not too bad for having 2 gigahertz wide bandwidth, for a matching network with an SMT component in between. All right, so we are done with final design. Now, if you just want to make sure this ground doesn't have any adverse effect onto your circuit performance, you can go ahead, switch on the EM simulation again, rerun the EM simulation, and then perform a co-simulation to make sure everything is okay. But just one caution here, when you have these many via holes, when you run EM simulation, you just need to do one thing in order to save a lot of your memory, is going to options, physical model, and this via holes, just switch them to lumped instead of 3D, because all these via holes are for grounding, right? So by doing this, you will save a lot of simulation time and memory and effort from your side. All right, so I'm not going to do that, but in case you want to go ahead and do a new co-simulation just to make sure the grounds is not too close to these transmission line to have some adverse effect. All right, so now the final step remaining is to export a Gerber file. To export Gerber file or DXF or GDS from ADS, you go to File, click on Export, and now you have variety of file formats to be selected. So I will go ahead and select Gerber and drill file format, and I would like to view this. So ADS has a Gerber viewer inside, and your Gerber file will be created inside the workspace folder you can see here, and it will create a folder called manufacturing, then your design name, and then there will be a folder called Gerber. Now the options of Gerber can be set from here, whether you need inches output or a MMS output. So mostly people use inch, but sometimes they use mm as well. You can set your precisions, what you want. If you have multiple layers, you can select which layer you want to generate Gerber for, whether you want to generate positive or a negative Gerber. Again, it all depends on your fab house. In the drill, so we have a drill hole on this layer, drill holes on the whole layer, and we can export those, and it will create an NC drill file. And currently we have 68 holes here. All right, so once you are done with the setting up options, click OK. And now you will have a Gerber file viewer, and this will be how your Gerber file will look like. And look on the table, you can switch on or switch off certain things, and you can only look at the files. Now, where are those files located? Very quickly, if I go to the main ADS window, right click, explore. So it will take you to the workspace folder. Under that, you have manufacturing, then you have your design name, and then you have this Gerber file. So you have con.gbr, whole.drl, whole.gbr, and you can just open them in a notepad editor if you want to read through. All right, so that brings us to end of this tutorial. It was slightly long tutorial, I know, but as you can see, we had plenty of things to talk about, and I gave you plenty of practical tips which will help you in doing this kind of matching network design, whether you are doing it for RF board, MIC networks, even if you are doing MMIC or sometimes even RFIC, wherever you need this kind of distributed matching network design. All right, so thanks a lot for staying till the end, and I hope you like the content presented. If so, give it a thumbs up and don't forget to subscribe to my channel. And last but not least, please go ahead and put this link on your social media or forums you are a member of and make sure this gets some visibility. And I thank you in advance for doing so again and wish you all the best with your matching network. And don't forget to put your comments in the comment description if you have any further questions for me. Thanks again.